Hello, grade 12s. I hope your studying is going well. This is an explanation of the electrodynamics question. A current carrying conductor, AB, is placed in a magnetic field. So this magnetic field exists, and we see that it is directed out of the page because it's a dot. If it was directed into the page, it would obviously be a cross. At point P, the resultant magnetic field is 0. So something must be cancelling out the magnetic field that is coming out of the page. And so at P, they must be experiencing a magnetic field into the page to cancel out the magnetic field that exists coming out of the page. So remember, if we've got a current carrying conductor, it has a magnetic field around it. And so in order to make the resultant magnetic field 0, it means that the magnetic field around this current carrying conductor must go into the page there at P to cancel the one coming out of the page. So we're going to use our right-hand rule, and remember our fingers are the direction of the magnetic field. So we need to point our fingers into the page and then look at our thumb. Our thumb is pointing in the direction of the conventional current, which is from B to A. And so what direction does the current in the wire flow? It's from B to A. Briefly justify your answer. It's because the magnetic field must be into the page to make the net field at P equal to 0. And I use the right-hand rule. Then the current carrying conductor experiences a force. Now remember, we are dealing with a piece of wire that has current in it. So there's a magnetic field around it, and it's placed in an external magnetic field. So those two magnetic fields interact with one another, and they cause the wire to move. So it's based on the motor rule. So we're going to use Fleming's left-hand motor rule. Remember, if they ask what rule, you have to use all of the words. You have to say Fleming's left-hand motor rule. So remember to put your thumb and your pointy finger at 90 degrees and your pointy finger and your middle finger at 90 degrees. And remember, your thumb will give you the direction of the force. So we have to take our pointy finger, and that must be directed towards us because the magnetic field is coming out of the page. And then your middle fingers must go from B to A because that's the direction of the current. And then you'll see that your thumb is pointing upwards. And so that's the force it experiences will be upwards. Then remember that force is determined by the current, the strength of the magnetic field, the length of the wire within the magnetic field, and then this sine theta is the angle between the wire and the magnetic field, the wire with the current in it and the magnetic field. And so this one says, name 2 ways that the electrostatic force experienced by the current carrying conductor can be reduced. So I like to look at this equation. So we need this force to be reduced. And so if we decrease the current in the wire, it will reduce the force. If we decrease the strength of the magnetic field, it will decrease the force. If we decrease the length of the wire within the magnetic field, it would decrease the force. Then a magnet is moved away from a solenoid. As the magnet is moved away, a current is induced in the solenoid in the direction shown. So this is a solenoid. So remember, in these loops of wire, we have current flowing. And so I want you to use your right hand and put your fingers in the direction of that current flowing. And then the thumb is pointing towards the north. Remember, it sets up what is like a bar magnet inside that solenoid. And so your thumb points to the north and the other side of your hand points to the south. And so by using that right-hand solenoid rule, then we get that inside here, the magnetic field that is set up is a north and on the right is a south. Now remember, if we are pulling a magnet away, according to Lenz's law, remember it sets up a magnetic field to oppose the change. And so if we just do the quick method, if we are pulling this magnet away, then what's going to happen? That south pole is going to want to pull it back. And so I'll discuss it now when we get to the question. I'm getting ahead of myself. So state Lenz's law. So Lenz's law, remember, it's the induced current. Be careful, it must be the induced current, not the induced EMF. Flows in a direction so as to set up a magnetic field to oppose the change in magnetic flux. So it says, is the north pole or the south pole of the magnet closest to the solenoid? So if we are pulling this magnet away and there's a south pole over there, that south pole would be trying to attract the magnet back. And we know opposite poles attract, so that pole of the magnet must be a north over there. Then a coil of wire ABCD is being rotated in a uniform magnetic field. So we are providing the mechanical energy. So it's being rotated as shown. So this side, the AB, is going up in the rotation, and the CD is going down in the rotation. So there isn't current in this wire as yet. The motion of the coil inside that magnetic field induces an EMF, which in turn induces the current. So this one, we are going to use the the right hand dynamo rule. And so the thumb is the direction that it's being moved. The pointy finger, again, is the direction of that external magnetic field. And the fingers are giving you the direction of the current produced. So if we just look at CD, we know that CD would be going down. So we've got our right hand, we're pointing our thumb down. We know that the magnetic field is going in the direction B over there. So put your pointy finger in that direction. And then you can see that your fingers are pointing down in this direction. This one you have to think about a little bit in 3D. And so you had to show the direction of the induced current caused by the induced EMF. Then state Faraday's law. It's the EMF induced is directly proportional to the rate of change of magnetic flux. Then it says, explain how an EMF is induced in the wire when it's rotated. So now remember, we have to be very careful with our wording here. So we first talk about the movement. So we're saying, as the coil is rotated within the magnetic field. So we focused on the movement first, and it's the coil that's being rotated in the magnetic field. We're not just rotating it in the air. It has to be in the magnetic field or nothing would happen. Then there is a change in magnetic flux. Where is that change in magnetic flux? Inside the coil. You have to have that wording there. Then, according to Faraday's law, a change in flux inside the coil induces an EMF. And in turn, first we have to get the source, which is the induced EMF, then we only get the current. Just think about it in a normal electricity circuit. You need the cells to power the circuit. Those cells give a potential difference. And so it's the same here. We get the induced EMF first, and then we get the induced current. Then the graph below shows the induced EMF against time for 2 complete cycles of this generator. On the graph above, draw the curve of EMF versus time when the speed of coil rotation is doubled. So we know from Faraday's law, we know that the induced EMF is directly proportional to the number of turns. So we haven't changed the number of turns. We also know it's directly proportional to the rate of change of flux. So now, if we have, it's the speed of the coil is doubled. So if we're doubling the speed, we double the EMF. So what was 1 block high must now be 2 blocks high. But remember, if we're doubling the speed, we're actually halving the time that this happens in. And so please be careful. Some of you lost marks because you can't be sloppy when you draw this graph. It has to be 1 block wide because originally it was 2 block wide, and we are doubling the speed, so now it must be half the time. And you mustn't be sloppy. It was 1 block high, now it must be 2 blocks high. So you must just be careful when you draw it. Remember, if you affecting the speed, it not only affects the EMF, it also affects the time. So if it was just you are just changing the number of turns, but it's at the same speed, then the time would be the same, and then we would just make it higher. The amplitude of the wave would be higher. Then here, a cell phone charger consists of a transformer connected to a rectifier to convert 240 volts, so that's our initial voltage, it's our primary voltage, to 10 volts. So we're reducing the voltage. So that would be our secondary voltage. If we were reducing the voltage, remember that's a step-down transformer. The number of windings on the secondary coil of the transformer is 20 turns. So that's it's NS, the number of turns on the secondary coil. And then they ask for the number of turns on the primary coil. So this one, very straightforward. We're just plugging in our values and solving for the number of turns on the primary coil. So remember, if we're doing a step-down transformer, the number of turns on the secondary coil must be less than the number of turns on the primary coil, which it is. Then, the cell phone charger works with direct current. What is used to ensure that the current flows through the cell phone charger in one direction? Refer to the diagram. So here in this diagram, this setup is called a full bridge rectifier. Okay, so it's not only just a diode, it's a setup where we get full bridge rectification. So it's a full wave bridge rectifier. Then, if the device mentioned in 7.4.2 were not present, the current through the phone charger would be AC. So this is what the current would look like. The charger would not work because the charger must have direct current in it. On the same graph, show how the current appears when the device mentioned in 7.4.2 is used. So this is full wave rectification. Remember, if it was just half a wave rectification, then it would basically just cancel these bottom ones. And then you would have there, blank, there, blank, there. But because it's a full wave rectification, it takes these crests and makes it a trough. And then you must make sure they all have the same amplitude. You must not be sloppy in your drawings. They must all look exactly the same, and they must all be on the one side of the x-axis. Yes, that was the last one. Thank you.